What's up, guys? This is Jahangir from Emporium, and today we're going to be talking about one of the biggest conceptual things you need to understand in physics, and that's motion time graphs. Now, there's three different types of motion time graphs that we just have to know. It's position versus time, velocity versus time, and acceleration versus time. Now, these motion time graphs really help us understand the correlation of position, velocity, acceleration, whether we're having positive, negative, speeding up, slowing down, all that good stuff. So first off, let's talk about position versus time graphs. So this is going to be our position versus time graph, X representing our position, T representing our time. And let's say we had something like this, just some curves over here. And let's just say we had something like that. So over here, as you can see, we have a sort of positive slope. So I'm just going to write this over here. So we have this positive slope going up here. Now, with position versus time graphs, always look at the slopes, whether they're positive, whether they're negative. So starting off from over here to up here, we have a positive slope. So we have positive slope. Since we have a positive slope, we're going to have a positive velocity. That obviously makes sense because our position time graph, the slope of our position time graph, so I'm going to write this over here, the slope of our position versus time graph is going to be velocity. And velocity, like we said, is change in distance over change in time. If we look at basic algebra, we know that our slope is always going to be our change in y over change in x, which is why our slope is going to be our velocity. So over here, we're having a positive velocity. Now we also have this curve over here. So these upward exponential curves are going to represent as speeding up. From this position over here, we have a positive slope, which means positive velocity, and we're speeding up. Now, these top points over here, and I'm going to write them as orange, these points over here are going to represent change in direction. So I'll put change in direction. So since we're changing in direction, we're having this, if we look at our x-axis over here, we're having a same x-axis. Our y-axis, my bad. So our position is not changing at this point over here, obviously, since we're changing direction. So our position over here is going to be constant. Now, let me write this over here. So if x is constant velocity, I'm going to say v equals 0 meters per second. Now the reason why, if x is constant, velocity is 0, is because, like we said, velocity over here equals our change in x over change in time. Since our x is constant, we'll say x is maybe like 8. So over here, x is just staying at 8. So it's consolidating at 8 meters or anything like that. So if it's staying at that position, then our velocity is going to be 0. And we have this change in direction, and we're going from a positive slope to a negative slope over here. So let me actually change this over here. We have a negative slope. So now we have a negative slope going down. So what does this mean? If we have a negative slope, that means we have a negative velocity. That makes sense because our slope is our velocity, like we said. And talking about speeding up and slowing down, when we get closer to this change in direction on our position versus time graph, this portion over here, we're going to be slowing down. So slowing down. The reason why is because not only are we getting closer to our change in direction, we're getting closer to our 0 velocity. We're slowing down because our velocity and acceleration are in different directions. Because as you can see, our velocity is positive, but our acceleration is going to be negative, so that's why we're sort of slowing down. Anytime we get closer to a change in direction, we're slowing down. Anytime we're getting farther away from that change in direction, we're speeding up. So you can think of it as like throwing a ball or throwing some sort of object. when you throw it, at first there's going to be a lot of speed until it gets to a certain point, which gravity as a force will act upon it, and it'll slow down getting up to gravity and just speeds down coming back down. So it speeds up coming back down. That's literally what we see in these position versus time graphs. And since it's slowing down over here, getting closer to that change in direction, we're speeding up, getting away from that change in direction because obviously since we're speeding up. Now we have another change in direction on the bottom over here. So we're slowing down. We have a negative slope, but we're slowing down and then we're speeding up going to the positive velocity. So number one thing you have to look at with all these position versus time graphs is look at slope. Look at the slope of these position versus time graphs, because it doesn't matter if this curve over here penetrates through the x-axis going to negative values, negative distances, because we're only looking at the slope. That's the only thing we need to pay attention to with these position versus time graphs. If you see these curves over here, then that means we have a change in velocity. We're going to have some sort of acceleration. So curves on a position versus time graph mean we're going to have an acceleration. If we have a straight line on our position versus time graph, this means we have no acceleration and our velocity is constant. Remember, when our position is constant, velocity is zero. When our velocity is constant, acceleration is zero. So that's one of the things you have to understand with these position versus time graphs. And now let's translate this entire position versus time graph into a velocity versus time graph. So this is our velocity versus time graph, and let's actually write down what that looks like. So I'm going to have on the screen a reference of our position versus time graph, and now let's sort of draw our velocity versus time graph. Now, on the first portion of our velocity versus time graph, we have a positive velocity. So since we have a positive velocity, we're moving up over here, and that velocity is changing. We're speeding up, so our acceleration is also positive. So we're going to have this straight line over here representing our velocity as a change. Because if we see these lines over here, if we saw like a horizontal line right here, that means that our velocity is constant and we have zero acceleration. And that's one thing I didn't really talk about in this position versus time graph, is that if we had a horizontal line, our velocity would be zero because, like we said, our position is constant. So that's representing our sort of horizontal line, saying that our position is constant. So anytime you see these just horizontal lines, that means constant. So since we have this straight sort of angled line over here, that's indicating a positive velocity, and we're speeding up since we're moving away from this x-axis. So one thing to note is that with these velocity versus time graphs, and let's say if we move away from x-axis, we speed up, and the opposite if we slow down. So I'll put if we move away from our x-axis, away from x-axis, we slow down. So we have a positive acceleration, we have a positive velocity. So we have positive velocity because we are looking at our position versus time graph, which was showing an increase in position. So that's our positive velocity. It was an increase. It was a positive slope, so positive velocity. We're also going to have positive acceleration. Now, if we look at our position versus time graph, we saw a change in direction. But before that change in direction occurred, we were slowing down. And then when that change in direction occurred, then we sped up. So change in direction is going to be represented when we penetrate through the x-axis. So this point right here, and I'll draw this in a different color. This point right here is now our change in direction. Change in direction. So before, our change in direction for that position versus time graph was at the top of the mountain and at the bottom of the valley. But now our change in direction is represented when we cross the x-axis. And this makes sense because our y-axis is representing our velocity, and we're decreasing in velocity until we get to a zero velocity, and then we start having a negative velocity. Remember, velocity shows us magnitude and direction. If we're going from a positive velocity to a negative velocity, then we obviously know we're changing in direction. That is why our change in direction is represented when we penetrate through that x-axis, when we break through the x-axis. So when that occurs, our velocity is still going to be positive because it's above the x-axis, because anything over here is our positive velocity, but our acceleration is going to be negative because velocity is changing from a high over here. Let's say this was 8 meters per second, and now we're going to 0 meters per second. So this is final minus initial, 0 minus 8, and let's just say that occurred in 2 seconds. So we're going to have a negative 4 acceleration, so meters per second squared. So that's just one of the things you need to know, is when we're getting closer to the x-axis right here, if we get closer, oh, sorry, I actually put move away from here. If we move, I just noticed that, my bad. If we move closer to x-axis, then we slow down. So I forgot to mention that. That's my fault. But if we move closer to the x-axis, we're slowing down. If we move away from the x-axis, we're speeding up. So when that occurs, and let me just erase this over here, we have a change in direction, and then we're speeding back up again. So that's showing that over here we have that negative velocity like we showed from the bottom curve. So we have negative velocity, but now we're going to be slowing down. So we get to this part over here, we have another change in direction, and let me move all of these words. So let me actually just X them out. So we know that our green is just going to represent our change of direction, and we're going to be going back up because our velocity went from a negative slope to a positive slope when we hit that bottom. Remember the bottom of that valley, which was a change of direction? We're going from a negative to a positive slope, and we're going from slowing down to speeding up. So this is what it looks like on our velocity versus time graph. Now, what about our acceleration versus time graph? So now let's look at our acceleration versus time graph. And to sort of draw our acceleration versus time graph, we need to base it off of our velocity versus time graph. And just like when we were basing our velocity time graph over our position versus time graph, this depends on the slope of our velocity versus time graph. So at first we have a positive slope, this indicating a positive acceleration. Then we have a negative slope, and we finally end off with a positive slope. So that is, and I don't mind the magnitude, like this acceleration is higher than that, don't mind that, as long as we know that we start off our position or our positive acceleration, then negative acceleration, then positive acceleration. So this depends on the slope of the velocity versus time graph. Now when we're speeding up and slowing down, this only occurs, well, obviously when we're looking at the x-axis. When we move away from the x-axis, we're speeding up. When we're getting closer to the x-axis, we're slowing down. And also, we're speeding up when acceleration and velocity are in the same direction. So if we look up over here, our acceleration and velocity are both in the same direction because we have a positive velocity, obviously since we're above the x-axis, and we also have a positive acceleration. We have positive velocity because we're above the x-axis, and we have a positive acceleration because we have a positive slope. Now, if we look down here, we have a negative acceleration because we have a negative slope, but we also have a positive velocity, which means that we're in different directions. Now, and that's why we're slowing down. But over here, we're speeding up because our acceleration is negative slope, and our velocity is negative as well because it's under the x-axis. So over here, we're slowing down because acceleration is positive, velocity is negative. Remember, acceleration on these velocity versus time graphs is the slope, and our velocity is negative because it's under the x-axis, so that's why it's slowing down over here. Then we move back up to positive acceleration, and we have a positive velocity, which both the same direction. That's why it's speeding up. So that's one thing to understand when we're talking about speeding up, slowing down. It only occurs, speeding up occurs when they're both in the same direction, when velocity and acceleration are the same direction, and slowing down occurs when acceleration and velocity are in different directions. So let me actually write that real quick, and let's write a couple of points that we have to know. So first, we have to know that acceleration, so I'll just put A, depends on slope in velocity versus time. So our velocity depends on slope in position versus time graph. If our position is constant, velocity equals 0 and acceleration equals 0. Now, if our velocity is constant, our acceleration equals 0. If velocity is changing, then obviously we have an acceleration that is not equal to 0. Another thing to note, we speed up when velocity and acceleration are in same direction. We slow down, and I'll just copy this whole entire thing over here, but when they're in different directions. So when velocity and acceleration are in different direction. I'll just put diff just to abbreviate. So we speed up when velocity and acceleration are in the same direction. We slow down when velocity and acceleration are in different directions. So when you understand these points right here, then it becomes very easy to interpret these motion time graphs. So hopefully that helped you guys understand how to navigate through these motion time graphs and how to create them. And as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.